Now the title of this video is a mouthful, but here's what I really want you to walk away understanding. When we describe where we think the electron's likely to be, we're going to use some nasty, very complicated equations to do it. Now, rather than deal with equations that look like this, and yeah, this is the simplest set. Later on this will matter for you. This is for the 1s orbital. Right now that doesn't mean much to you probably, but we'll see something about that later. If we were to take this function and this function and substitute it into these two spots, we would get this expression right here. If you then square that, you'll get your electron density probability field. Now, we probably don't want to do that. And also point out that we have some subscripts in this equation that help us keep track of our variables. What we're going to be talking about here are quantum numbers. Those quantum numbers are the subscripts in these equations. It turns out, though, that they end up being a very useful shorthand for trying to describe things, so we don't have to use those equations you just saw. So, despite the amount of memorization that does come alongside of this, and there's a little bit to it, but not a ton, please recognize that we are simplifying life for you by not having you go to those equations, and that there's a reason for what you're doing. Now, the nice thing about the orbitals is they're going to let us visualize where the electron's likely to be. And the quantum numbers we're going to describe will act as an address system that let us communicate where the electron's at, and for the region of space that it's in, what its size, its shape, and the direction it's pointing will be. So the first of these quantum numbers is going to be our principal quantum number. Now you remember when we said we had our nucleus and we put some orbits around it? We said that the first one was n equals 1, second one was n equals 2. This is the same kind of idea. Now we're way past orbits. We are talking about orbitals, but still that basic idea does still exist. The principal quantum number, n, is telling us something about how far out the electron is. So if you go to a higher one, you're at a higher energy. That's a good starting point for it. This is going to be the first of our numbers. In fact, some might say it's the principal of those quantum numbers. That's where the name came from. Now next up, once we get within one of these shells, the quantum number, the principal quantum number, we need to describe something about the shape of it. And what we're going to see in other videos is that there's going to be a couple of different shapes for these sort of things. Now, just picture for yourself what things will look like if they're sticking to something but still moving around. Well, one example would be to have something and you're going to move around it like a sphere, right? You could also have something more complicated where you end up kind of making a figure 8 around it. You can get even more complicated sets of orbits around things, and that's what we're talking about with orbitals. Angular momentum number, cursive L, tells us something about these shapes. Now, principal quantum numbers were just whole numbers, 1, 2, 3, all the way out to infinity. Angular quantum numbers, we're going to have a different number available depending on how far out we are. Now, hopefully that makes a little bit of sense. Picture that you're roller skating or ice skating or something, and you're doing it in a space smaller than my office. You're probably not going to be doing too many complicated things. You're going to stay in pretty much one shape. What if I put you into a half-court basketball space for your ice rink? Well, now you can start doing some more interesting patterns, right? If I give you an entire ice hockey arena, you've got a lot more space to put in those patterns. You can still do the simple ball shape. You could start doing some dumbbell shapes. You could start making big clover leaves in each of these bigger sections. That's the idea that we're having here. So angular momentum number is always going to be starting at the number 0. And then we're going to count up to one value less than this value. What we're saying basically is that if I have a small room, I can only do one shape. If I have a slightly bigger room, there's 2 possible shapes I can do. If I have an even bigger room, there's going to be 3 different types of shapes that I can do. And actually, it's going to get a little more complicated than that, but that's the idea behind it. We'll also see how this does some branching in another video where I help you connect the dots on this a little bit. But that's the idea. Whatever quantum number you're at, your angular momentum quantum number, cursive L, can go from 0 all the way up through one value less than your quantum number, your principal quantum number. Now there's a third one. Of course there is, right? For the angular quantum number, you can then take it plus or minus that value around 0, and that's called your magnetic quantum number. It actually doesn't have much to do with magnetism. It's there because it was named for historic reasons, based on some observations we had, and I'll leave that description right there. So suppose we had n equaled 3, and you see me having this written out after these in the notes. N equals 3. That means that there's also an n equals 2 and an n equals 1 inside of that. Just like, we had with our plus. You can have ring number 1. You can have ring number 2. Further out, you can have ring number 3. Within ring number 3, principal quantum number 3, I'm going to be able to have L equals 0, 1, and 2. I stop just before I get to the value. Also notice that I end up having, hey, look at that, 3 values, just like the number is. That's how you can remember that piece. Now, if I've got 3 different shapes, now I got to think about how they can point in space. For each of these L's, I'm going to be able to have a different set of magnetic quantum numbers. If I'm talking about L equals 2, I'm going to be able to have it do, and I'm doing this for the magnetic quantum number, so I'll do this one down here, but I'll need more space in a moment. We'll do a -2, -1, 0, 1, and 2. So notice, for L equals 2, we get a total of 5 ML values. For L equals 1, we're going to get -1, 0, +1. We're going to get 3 from that one. For L equals 0, we're going to get just 0, because plus or minus 0 around 0, 0. That's our magnetic quantum number. Now there is a 4th one, and the book doesn't always point it out right there afterward because it took a while to get there conceptually and also mathematically and in the science. But I think it's easier for us to see all the quantum numbers simultaneously. So let me point out something. If I take some hydrogen atoms, 1 proton, 1 electron, and I shoot them in a beam through a tiny little hole, and I put them through a magnetic field, something interesting kind of happens. Half of the atoms curve up, 50% of the atoms curve down. So you've got a 50-50 chance of being either one. It's almost like there's a north pole and a south pole on the electron. Almost like that. That's not actually what's going on, but we're still going to pretend like it is because the mechanics for what's going on there get very funky and not Chem 1 appropriate. Well, we have a quantum number to explain that, and that's called m sub s. Magnetic quantum number is m sub s for spin. So you can see it's going to have a magnetic pole, at least we can think of it like that, called spin. It'll be called our spin quantum number m sub s. It's got a value of either plus 1/2 or minus 1/2. How do you know which one it is? Well, if you're doing an experiment, you get to define it based on whether it curved toward the North Pole or toward the South Pole. I'm not going to ask you about that. You will just pick which one, because remember, every atom has a 50-50 chance of having each electron have one or the other. So we'll pick them at random. Most people just tend to say that it's the plus 1/2 because we're used to writing plus. The second one that they'll write in, they'll put as the minus 1/2. Totally fine as a problem-solving approach. Just remember that really, though, you should be flipping a coin every single time you write it down to decide, is it plus or minus 1/2? Because there's still a 50% chance the atom has it that way. So those are going to be our 4 quantum numbers. If we look at later videos, you're going to find out what that leads to in terms of shapes and orientations in space.